first lecture we're going to do today. We're going to talk about physical properties of urine. So Donovan, this will be your answers will come here. We talked a little bit about this yesterday in lecture 1 and 2. We had a little bit of talk. We're going to get into a little bit more detail in this lecture. So urine's physical properties, the things we're looking at: color, volume, transparency, odor, foam, and concentration. Like I said yesterday, we are not going to be wafting those urines and smelling those urines, but let me tell you, sometimes when you open that container, you're going to know. Okay, it's just things just kind of happen. So when we're talking about volume, normal urinary output is between 600 and 2,000 milliliters per day on an average of 1,500 mils every 24 hours. So like I said yesterday, another day, another 1,500 mils. 24-hour urine volume we report out by milliliters per minute. We have to calculate how many milliliters per minute because we calculate everything by minute, because remember, 24-hour urine usually is not going to be exactly 24 hours, right? They're going to start it at 6:30 the first morning and end it at 6 o'clock the next morning, or they might end it at 7 o'clock the next morning. So again, you do that calculation of 1,440 minutes in a 24-hour period based on, you just have to calculate on the side of the jug. Again, when you're doing a urine like that, most of the time the biggest problem we're going to have is patient accountability. There, patient issues with keeping track of what time did you start it. They're going to want to say, oh, they wanted me to be 24, so I'm going to lie. That sometimes happens. So it's really important to make sure the patients have good instructions, because compliance with any sort of at-home collections can be difficult. So terms related to volume: polyuria, poly, lots, excessive, urea, pertaining to the urine. Again, med term. If you don't remember, go back to your BLS and break it down. Excessive output, excessive urinary output, greater than 2,400 mils every 24 hours is what you're looking at when that type of situation. We see this oftentimes in diabetes in particular. And there's two types of diabetes that we see this in: diabetes mellitus and diabetes insipidus, okay? So diabetes mellitus, that's the one we think of most often when we think about diabetes in this country. It's the one that we see most often in the older adults, things like that. Inadequate insulin or inadequate ability of the insulin to work. As you get older, that kind of is what we see more of. What happens is that renal threshold we talked about yesterday, 180 milligrams per deciliter, your sugars get so high that renal threshold, it can reabsorb that up to 180 milligrams, but it can't do the rest. And that's when we're going to have excess glucose in the urine. And remember, we talked about that osmotic change. The excess water is going to be trying to dilute that urine out because there's so much sugar into it. So because of that, the body is constantly sending more water out in the urine, trying to balance that out. Diabetes mellitus literally translates to honey sweet. It's sweet diabetes. Diabetes insipidus is inadequate ADH, antidiuretic hormone. So if you remember, the antidiuretic hormone is what's going to prevent us from peeing a lot, right? And so antidiuretic hormone comes in to help hold some of that water back, help reabsorb more of that water, help us keep hydrated. Diabetes insipidus is a situation where you don't produce the antidiuretic hormone, and therefore you're urinating a lot more. Loss of fluid is polydipsia, and so you end up drinking. That's where you drink lots of water. So you're drinking a lot, trying to keep up with, you're feeling dehydrated all the time because your body's not holding water. It's not retaining any water. We're constantly losing water. That's insipidus. Insipid is bland. So bland diabetes. One way to distinguish the two, we're going to look high specific gravity of diabetes mellitus due to glucose. Now, when we're talking specific gravity, we're going to talk about two types of specific gravity today. We're going to talk about refractometry, and we're going to talk about the strip specific gravity. So when you're talking about specific gravity in this situation, you're talking about the refractometer, and we'll talk about how that works in a few minutes, in a few slides. Diabetes insipidus is going to be a low specific gravity because it's going to be so diluted. Your urine is going to be more like water, versus when you're losing sugar, the glucose is a big molecule and causes the refractometer to be a higher result. Again, we'll talk about refractometry and strip specific gravity in a few minutes. More terms. There's lots of terms to learn in this program, right? Get your flashcards going. I recommend it. Color code them. Urine, buy a pack of yellow. Hematology, buy a pack of pink. Just kind of keep your. Does anybody actually use flashcards anymore? Okay, I'm a big flashcard person because that's just how my brain works. So color coding flashcards is a great way to do this. So diuresis, yeah.
I recommend the ones that are spiral bound because you can just flip
Ooh,
perforation to tear off.
nice. Okay. So spiral bound note cards. I didn't even know those existed. So good. And they come in all sorts of colors now. I color code everything. You're actually going to see in my pocket in lab, I have a yellow card that has all of my lab notes that I need to remember for urinalysis. I've got a red one for my hematology notes. Phlebotomy, I think is purple if I'm not mistaken. I don't remember because there's certain things I had to like remember when I don't do it very often. So I have them in the little plastic sleeves in my coat pocket. So diuresis, increased formation of urine. Diuretic, something that causes an increased amount of urine formation. Oliguria, less than 400 milliliters per day of urine. And that things you're gonna see shock, nephritis, things like that, where your kidneys aren't allowing the water to go through. Your kidneys aren't functioning well. And so because of that, you're not having as much water. Dehydration. Remember yesterday I talked about those iron people? Those iron people are oliguric, right? They're, when they finish the race, they're getting fluids because they are so dehydrated. They're not urinating for that entire stretch. Anuria. Anytime you see a in front of a word or in front of a word, the in is if the next word is a vowel. So urea, so it'd be anuria versus anuria or auria. If there's two vowels together, it'd be like auria. Of course, that doesn't make, so it's anuria, right? So a or an, when you see that before a word, it's lack of. Okay, we're gonna see that word, we're gonna see that a lot throughout all of our programs. So a or an means lack of. So anuria is the absence of urination. And we're gonna see this when we're in severe renal diseases. Your kidneys aren't working. So we talked about how much it filters the blood and how much blood filters through the kidneys on a regular basis. Well, when they're not working, things aren't filtering through and we're not getting any urine production. Nocturia is when we have increased urination at night. Noct is night. So things like prostatitis and pregnancy are two different times in particular that we will see more of that. Now, normal urine color, I talked about yesterday, urochrome. Urochrome is the one you need to know. Urochrome is the primary pigment that causes urine to be the yellow color that it is. Most urine is anything straw to amber. Like I talked, anything is normal because it just shows hydration status most of the time. There are other things that are involved in urine color, urobilin and urourethrin, but to a much lesser extent. The primary cause of the color of urine is urochrome. Chrome is color, urine, urine chrome. You will see that again. So make sure you know what urochrome is. So urochrome is the kidney produces the same amount consistently throughout the day. So if you never changed your hydration status, like if you didn't eat or drink anything and you were stuck to an IV giving you the same amount of fluid all day, your urine would stay the same, and you urinated every hour, for example, it would always be the same. We all know that there's a lot more involved in that, and that's why we get the different colors that we get. Abnormal colors. Amber urine, sometimes we'll see that with real concentrated urine, like when you get super dehydrated, like when you get the flu. You guys you don't feel well, you're not drinking, you're not eating, you get super dehydrated, your urine becomes like a real amber color. The other time we'll see that is bilirubin. Now we talked about bilirubin yesterday and we talked about it in basic lab skills, right? Or phlebotomy probably. Bilirubin, when you get that icteric serum, it's that same color in the urine when it's high in bilirubin. If it's brown or yellow or green brown, it can be bilirubin or biliverdin. That's a breakdown of the bilirubin. We'll learn about that a little bit later too. When it's orange, like an orange red or an orange brown, a lot of times that's going to be urobilin. When it's bright orange, it's this drug, pyridine. It's a drug you can get over the counter. We'll hopefully get an example of this year. And people take it when they think they're getting a little bit of a UTI, especially chronic UTI users, and it'll change the pH of the urine and hopefully kill the bacteria. But it stains everything orange. Like the side of the containers get this like deep orange color. When you go to dip a urine, everything is crazy. I would never give you one of these on a test. I never will trick you on a test, but I will try to make sure we get one so you can all see how crazy. Like if you get a strip that you can't read, and it's this crazy orange color, that's what we're looking at. Yeah.
I had one come through the lab the other day and spilled some on the counter. You have to like scrub it off.
Even if you wipe it right away, it like seeps in any porous. It is the craziest stuff. Huh? People have been using it for years.
Okay.
And I don't remember the exact like how it works. It's really fun. You can buy it on Amazon. And I was laughing to Marcy. I said, to make sure we always get this in a urinalysis class, we should just buy a pack and one of us should take one day just so we can get a sample of it. It's crazy. They know we like it in the clinic, so hopefully we'll get one this year. Red. Anytime you're seeing red, you're gonna think blood. Any kinds of reds. So you get clear red and cloudy red. So clear red is hemoglobin. So when you have something like hemolytic anemia, for example, where the red cells are lysing in the bloodstream, that hemoglobin is going through the kidney, through that glomerulus, and it's gonna be a clear red. Cloudy red is where it's gonna be cells. So if you go to swirl it, when we get a urine, we pick it up and we swirl it. And when we swirl it, we want to see kind of what's happening with it. And if it's kind of cloudy, sometimes you'll see the cells settle and they'll kind of fill back in. So if it's cloudy, a lot of times it could be the red cells we're looking at. Dark red-brown could be myoglobin, and that's muscle breakdown. We see myoglobin in things like excessive exercise. There have been a couple of case studies on CrossFit? Yeah. Where they have people designing the exercises that don't understand the physiology. They've gotten better because of this. And they end up getting this rhabdomyolysis, which is muscle breakdown. And because of that, the body's trying to excrete this myoglobin and get rid of this toxic myoglobin in the body. And we can get this dark red-brown. Dark red or red-purple, we see porphyrins. In hematology, you guys have talked about porphyrins now, so you understand where porphyrins are. Black, dark brown or black, melanin sometimes, homogenic acid, or phenopoisoning we sometimes see. So all of these are abnormal colors of things we see. Now, again, this is just a summary of that, your abnormal colors. Now, however, some other abnormal colors we're gonna see include blues, greens, things like that, medicines, vitamins. Anybody here ever take a vitamin B? Their urine turns fluorescent yellow because it's a water soluble. We take it, it flushes out what our body doesn't need. Lots of other vitamins, things like that. Birth control makes it kind of this green, blue color sometimes. So ingestion of foods, medicines, things like that can cause different colors. Yeah.
Under the red color, it says urates. What does that
mean? We'll talk about that when we get to crystal.
Okay.
Crystals. So what urates are, they're brick dust, and that's when we swirl them, they kind of come up and it looks like literal brick dust. And then as you watch, it'll settle back out. So there are some, and that's cloudy red, but it's like a brick red as opposed to a red. Okay. Yep. So that is another amorphous urates we'll talk about with crystals, but that is another one. Good. Okay, clarity. How well can we see through this? A normal clean catch urine that is properly collected should be clear. We should be able to see right through it. Now remember yesterday I talked, a lot of times the containers that we collect these urines in actually have a cloudiness to them. And if it has a cloudiness to it, we have to mentally tear, T-A-R-E, that cloudiness off of what we're looking at. So when we're looking through it, is it any cloudier than the container itself? If not, it's clear. Sometimes we get things with poorly collected urines, things like your epithelial cells. Remember I talked, our body's full of sloughing epithelial cells all the time. That's why with a midstream, what we do is we urinate a little bit, we flush those epithelial cells out that are the transient ones, and then we're only gonna get the ones that are more serious. Mucus, fecal contamination, sperms, powders, lotions, creams, all of these things can make a urine cloudy. When you have a urine sitting, if it's not properly stored, properly handled, we can get these amorphous materials that'll precipitate out. And that's the amorphous urates or amorphous phosphates. That'll depend on the pH. Again, we'll talk about that when we get to that point. Amorphous urates happen in a acidic urine. Amorphous phosphates happen in a basic urine. Also bacterial growth. If that urine sits on the counter for a while, remember I talked yesterday, urine is a great media for bacterial growth. So if that urine sits on the counter for too long, that bacteria is going to overgrow it and it's going to make it cloudy. So all sorts of things can actually make it cloudy over time. So terms that we use, clear, which is our normal urine, and then we use hazy, cloudy, and turbid. In our lab manual, it talks about clarity and the terms that we use for it. When you get to lab tomorrow, you will have to look at color and clarity. And the clarity, one of those four, is what we use. Now, out in the real world, you will follow your facility's policies wherever you're at. They may just use clear or cloudy. They may have 6 different variations. They may use a 1+, 2+, 4+ system. Follow us out there. Here, clear, hazy, cloudy, or turbid are the 4 that we use. As I said, mucus, amorphous phosphates or urates, sperm, crystals, bacteria, pus, blood, fat, casts, all of these things can affect the clarity of a urine. And we will go into all of them farther along. Every one of those we'll get deeper into as we go on. So, clear, transparent, you can see right through it. You can read through it, whatever. Hazy, we can still see the newsprint, it's visible. Cloudy, the newsprint becomes kind of blurred, and then turbid, you can't even see through it. Now, urines with blood. On the left side here, this is what fresh blood with cells intact. See how cloudy that is? Versus the center one, see how it's clear? It's your hemolyzed blood. So the cell walls have been broken up and hemoglobin has been released. So that was the question you asked. We got the cloudy red versus the clear red. We're looking at cells versus hemolysis. On the right side, it's an old blood and it turns kind of a brownish color, especially in acid urines. So that can affect the color when you're looking at an older urine. So odor. Not all urines are going to smell the same. Most of the time, it's kind of an aromatic kind of a smell. Smells that are not normal, ammonia, putrid or foul. Those we'll see a lot of times with bacterial infections. Sweet or fruity. Sweet or fruity we see with diabetes. So remember we talked yesterday about pouring the urine if the animals come, if the bugs come. It's a sweet urine. So if it's like a sweet or fruity type smell, we're looking at possibly a diabetes. Maple syrup. There's actually a disease called maple syrup urine disease, and we catch this usually in infants. They're unable to metabolize some of the amino acids to make in proteins. So the protein breakdown, they have these amino acids kicking out, and it smells like maple syrup. We pick this up on a newborn screen, but oftentimes nurses will notice it changing a diaper. The baby smells maple syrupy, so they're able to pick it up even earlier. Musty phenylketonuria, which is the inability of breaking down of phenylalanine. And you'll notice, does anybody here have a diet soda in a can? Nope. I don't see any around. Okay. It's just really funny. Over the last 10 years, I've seen way less soda and way more water, which is great for everybody. But if you look on the side of a diet soda can, it says, warning, phenylketonuriacs. This item contains phenylalanine, because they've realized that phenylalanine is makes it taste sweet, so they use it in diet sodas. I don't understand all the chemistry, but it has that warning on the side. So if you are phenylketonuriac, you cannot actually drink a diet soda. But those diapers, those babies smell musty, is one of the things we see with that. And then other orders from foodstuffs. Asparagus. You guys have all heard about asparagus, right? You eat too much asparagus, your food, you're going to have foul smelling pee. Other types of food things will also have similar issues. So normal, aromatic sweet, ammonia, ketones, maple syrup, and musty. Let's break down what we just talked about.
Okay, so I know that foods and medications can cause the urine to smell different. Is that just because that particular compound in that food or medication just doesn't break down in the body and that's how it's gotten rid of?
Or the breakdown products, because asparagus pea doesn't smell like asparagus. It's just one of the breakdown products of the asparagus that doesn't break down enough that comes out in that odor. Okay. Foam. When we're looking at foam, shaking or vigorous voiding. So again, we pick up the urine cup and we give it a swirl, and we're gonna look for foam on the top of the urine. When we look at foam, what we're looking for is foam that hangs out. I can make bubbles appear, right? I can take anybody's water here and we make bubbles appear and they go away. This is actually foam that sticks around. Think of a head of a beer. Is everybody here 21? Is there anybody not 21? Okay, so you've all seen a beer, right? Okay, so the foam on the top of a beer is what we're looking at. When you get that nice head on a beer, it hangs out, it sticks around. Not, oh look, there's bubbles. Okay, there's definitely the difference. So you can see here what this one's a little bit harder to see. This is yellow with white foam, and this is amber with kind of an orange foam. When you have this white foam on a normal urine, that we're looking at most times is going to correlate to protein. There's protein in that urine. This one with an orange foam, that most of the time is going to be bilirubin. That's going to correlate to bilirubin. So every urine, when we first get it, we look at color, clarity, and we give it a swirl and look for this foam. And the foam gives us a clue that we're going to find something else in the urine. So we always note those three things. So I got a case study. We have a urine specimen is obtained on a 50-year-old woman who has intermittent upper abdominal pain for the last 10 days. She's obese, she appears yellow, and has right upper quadrant tenderness. Physical appearance in the urine, the color is brown. There is a large quantity of yellow foam, and it's a clear urine. Which chemical test would you expect to be positive? Bilirubin, correct. So, bilirubin, good. You will learn more. We will have an entire lecture on bilirubin coming up, but amber foam, you're gonna think bilirubin, good. So the brown to amber color of the foam is suspicious for the positive bilirubin that we're seeing there. Urine is found in, with gallstone problems oftentimes, and it's the 4 Fs. Female, fat, 40 or more, and fairer skin tend to have gallbladder problems. So just one of those like little things when you see these, a lot of times women in their 40s and 50s in general start having gallbladder problems. It's just very, very common. This is, again, a picture of that urine with the longer lasting yellow foam. It's not just going to come up and go away, it's going to hang out. Key terms for this lecture, make sure you go through all these terms, make sure you know what they all mean, break them down. Urinary objectives for this lecture are all right there. And again, all these objectives are listed under the documents of your Blackboard. If you click on documents, all the objectives for every lecture is on one sheet. Highly recommend you print those off and study from those. Okay, we're going to jump right into the specific gravity. This is the second part of this first lecture. So, specific gravity. The definition, ratio of a mass of a volume of a solution compared to the mass of the same volume of water. Okay, it's under a certain temperature. Room temperature is where we fall through. No, what's different about room temperature? Sometimes this room is really cold, sometimes it's really hot, right? But on average, it's room temperature. Why does that matter? Why does temperature matter?
Can it affect pH?
Not quite pH, but if you think about as water gets colder and smaller and ice and boiling, the mass and how big it gets and how it expands and contracts, that's affected. So it's not quite the pH. Okay, we're going to kind of buzz through that. So the mass, weight of the volume is affected by temperature. What constitutes, if you look back at the urine system, urea, nitrogen, uric acid, and all these other products there. How does specific gravity relate to density? It's comparing the density of urine compared to the density of water on the same conditions. The good things is if as long as the urine is room temperature, remember yesterday I talked, if you pull a urine out of the fridge, you have to let it come to your room temperature to test. As long as they're the same temperature, we're going to be okay. So clinical significance, normal is 1.003 to 1.035. Water is 1.000. Huge range. Why do we care? What does it matter? Right? And it's all normal. That whole range is normal. The strips will tell you that whole range, but it's all normal because it tells us about the concentrating ability of the kidney on a regular basis, right? So if you're always really high or always really low, we know that your kidneys aren't able to adjust to what's happening in the rest of the body. So first morning specimen, we expect it to be high. It's concentrated. It's been sitting there a while. If you're really lucky and don't have to get up all night, it's been sitting there all night, right? 24-hour time specimen, we expect it to be 1.015 to 1.025 because over the day, it changes. If you bring it in and it's really, really high for the whole day, what's going on? If it's really, really low, what's happening? A random urine specimen can be all the way, anywhere in the range, because it just depends on how hydrated you are at the minute, what you've had to eat or drink that day, what time of day, how active you've been. You know, if I always joke, if you're a first grade teacher, you don't get to go to the bathroom all day, right? You know, you've seen the jokes about that, but it's true. You know, you pee twice during the day. Your urine's gonna be more concentrated than somebody who can go to the bathroom whenever they want. One note, when we're looking at specific gravity, we do use all 3 spots to the right. So if it's 1.030, we put that 0 on. We don't just stop at 1.03. We always use all 3 spots. So the normal solutes in a urine, we talked about this yesterday also. Urea, uric acid, creatinine, salts. Which one of these constitutes the highest quantity next to water in the urine? Urea, right. Good. Water's first, urea second. The other ones are all kind of close. Protein metabolism, purine metabolism. Where do these all come from? Muscle growth and muscle breakdown, right? I mean, you're building a muscle and breaking muscle down. Which one of these are going to ionize? Any of these on the side? These are your ionizable ones. Which ones do not? These guys up here do not. So the clue is anytime you have the little pluses next to it, those are ionized molecules. So we already just answered all that. Now, abnormal solutes that might be in the urine, things that aren't normal that will affect specific gravity. Protein. Remember, protein should not sneak through the glomerulus. If the albumin starts showing up on the stick, it means that you got holes in your glomerulus and the protein is now coming through. Early sign of kidney disease. We should not see protein in normal urine. Glucose. Normal healthy urine, we shouldn't see glucose because our body should be totally capable of reabsorbing that glucose all in. It's only when that glucose is really high or there's something wrong with the kidney where we can't reabsorb it that we start seeing actual glucose in the urine. Bilirubin. Bilirubin should never be in the urine. It means there's something going on in the body. Fats. We should almost never see fats. When you see fats, you got a big problem. We'll talk about that many lectures from now. X-ray contrast media. This is one of my favorites. It's going to take your specific gravity and bump you up to 1.060 sometimes. This is why, after you have like a CT with contrast or whatever, they're like, drink plenty of water. Please drink plenty of water. Get that stuff out of your system. Because it's not only is it just going to affect our labs, it just can't be good for you to have that hanging out in your body, right? X-ray contrast media will affect specific gravity. Bless you.
Thank you.
Now, on the dipstick, which one of these is going to be tested for? We're going to test for protein, glucose, and bilirubin on the dipstick. Fats, we can see microscopic. X-ray contrast, sometimes it makes little crystals in your urine. Sometimes it doesn't. We really just see it specifically on the specific gravity.
What is your idea with specific gravity when it comes to on the dipstick? Because it usually gives a range on the dipstick. Do you think it's accurate or not?
Okay, what's the...
On the dipstick, there's a specific gravity.
Yeah.
Little...
We're going to talk about that. We're going to talk about that.
Okay.
Because there's a difference between how the dipstick tests and how a refractometer tests, and that's coming up.
Okay.
So we'll get into that. Good question, good pickup, because that gets really confusing. We're going to spend quite a bit of time talking about that. So we talked about that. So terminology of specific gravity of the glomerular filtrate. So normal healthy person, when that glomerular filtrate gets squeezed through under pressure at the very beginning is 1.010. That we call isothenuric. Iso means the same. So isothenuric, 1.010. So if your urine that comes out at the end is 1.010, we consider that isothenuric urine. It's the same as the glomerular filtrate. Hypersthenuria, greater than 1.025. That means it's consistently higher specific gravity. Hypo, low. Hyper is high, hypo is low. Those are terms you got to get straight. You're going to see those over and over, and you've already seen them, I'm sure. Hyper is high, hypo is low. Hypostenthenuria is less than 1.005. So iso means same, hypo means low, hyper means high. Know those prefixes. So causes of isosthenuria, sometimes you're going to see isosthenuria when you're having tubular failure. Your body cannot secrete or reabsorb. So it comes out, it goes through the same way. Causes of hypersthenuria, the higher concentrated urine. Dehydration. Diabetes mellitus. We'll talk about that with the strip in just a minute. Kidney disease, liver disease, adrenal insufficiency are all things that can cause hypersthenuria. Causes of hyposthenuria, diabetes insipidus, kidney failure, excessive intake of fluids, and diuretics can all cause those. So how do we measure specific gravity? There are direct methods and indirect methods. Our direct methods are when we actually do the refractometer, where we actually compare the density to pure water. Okay, urometer, falling drop, harmonic oscillation. Most of these are not used anymore. Sometimes we'll see harmonic oscillation some places. Some places still have these hanging out, but most of the time they're not validated and they're in a closet somewhere these days. We just don't use that. Now, indirect methods, we measure some other property related to the density. So, refractometer and the reagent strip chemical method. These are the two that we use most of the time in the lab. These are the two that we're going to spend most of our time talking about. So the refractometer, this is a picture of a refractometer. Ours are on stands. Some of them are just sitting in drawers in the labs. Sometimes I have students that go to clinical and they're like, oh, we have one of these? You know, the techs have no idea it's in the drawer because they never use it. So the principle is we measure the refractive index of a light to the air and the velocity of light solution compared to water. So QC, we do this every day. In water should be 1.000, and then the sodium chloride solution, we use 5% sodium chloride. In our lab, it should be about 1.024. So what we're looking at is, as you're going through, we're looking at the light beam refraction. That's why it's called a refractometer through the urine. So normal air or normal water would be right here, right? It's a nice straight line. We are looking for this bend in the line. The more it bends, the higher the refractometer reading. So temperature could affect this, but the depth under the plastic cover is so small, it's not going to affect us too much because it comes to room temperature pretty quick. We put a tiny little drop under the refractometer and we put the lid down and we look at it. Have anybody here looked at the videos for tomorrow yet? The lab videos? Make sure you watch those lab videos before you come to lab tomorrow. There is one on the refractometer, how it works, and I talk a lot about how the refractometer works. The more dense the solution, the higher the angle of the refraction. So, the back of the refractometer, there's a little light switch that turns the light on.
Oh, there you go.
Okay, that was weird. Okay, there's a little light on the back. We clean this up. This is the little plastic cover. We clean it up with just a chem wipe. You can use actually a chem wipe for it. What is going on with my screen? Cord must be a little loose. Okay. See what's going on. Anyway, chem wipes or other absorbent paper, we do not have to use lens paper on this. Like we use lens paper anytime we touch a microscope. We don't have to worry about this. We use regular chem wipes. And we just use deionized water and the sodium chloride for QC, and we just use deionized water to clean it. We do not use our chemical disinfectant on the refractometers. So we turn it on, we lift the cover, we kind of clean everything with a little distilled water, and then we flood the refractometer with distilled water. So you take it, there's a little notch right here on the top, and you fill it with distilled water, and it should be 1.000. In the lab, I always have you do the sodium chloride first, because when you're first looking, it's going to be really hard to see that shadow look. The distilled water is going to be up about this way, right around this area. So you'll see a white on the bottom and darker on the top. It's much easier when you're first learning to use the sodium chloride first and then the distilled water. So then we're going to check the 5% sodium chloride, and we got to make sure the readings are about the same. Otherwise, there's an issue with the refractometer. Empty refractometer has a cloudy lid. The full refractometer, the lid gets dark. That's how you tell it's nice and full. You want to make sure that there are no bubbles in here. So sometimes you have to like tap the plastic a little bit to get the rest of the urine to fall all the way down. So what you can see here, here's our sodium chloride. So you can see it's darker on the top and lighter on the bottom. So I have you guys start with that first and then do the water. Then you're gonna clean it with distilled water, and then you're gonna test the urine specimen. And in this situation, you can see the urine specimen is 1.030. You're gonna read it up there. These take practice to learn to read. We will have time in lab. You'll actually have opportunity tomorrow to do all 5 of your urines. You will do refractometer on, just to make sure you're learning how to read it. Excuse me. When you are done, you lift the cover and clean it with distilled water. You're just gonna flood it with distilled water. There's a little cup right here. It's a little plastic cup. At the end of class then, you'll rinse that out, dry it out, and put it back, because it catches all this flooding that you're doing. It's gonna catch it in that little cup. Now, if you have a refractometer reading of 1.030 or 1.035 or greater, it's gonna be too high, you have to dilute it. So when you're diluting it, there are instructions in your lab manual for dilutions. I never expect you to know how to do everything. The lab manual has all your instructions. You'll have your lab manual on your exams. You'll always have your lab manual available for labs. So you're going to dilute the urine specimen. It tells you in your manual how to do that. You're gonna read the specific gravity, and then you multiply it by the dilution factor, just the right 3 sides. Usually we do it 1 to 1, so we have a 1 to 2 dilution, and so we'll take the right side and dilute it, multiply it by 2. We're going to report out the corrected specific gravity then. So here's an example. Our specific gravity reads at 1.035, so we have to dilute it. We decide to dilute the sample times 2. So we're going to take 1 ml of urine and 1 ml of deionized water, which is a 1 to 2 dilution. You guys have all had math. You should know that now, right? If the dilution then reads a specific gravity of 1.020, we're going to take this last 3, multiply it by 2, and now the reading is actually 1.040. Okay? We'll have some time tomorrow. You'll actually have one of these in your lab tomorrow, at least one, where you'll actually have to do a dilution on, just to kind of work your way through it. There's quite a few homework problems, well, at least 1 or 2 at least, where you have to go through and do this. Study guide has some of them. So in this situation, it reads greater than 1.035. We decide to dilute the sample by 3. How are you guys going to make that dilution?
2 mils of water, 1 ml of sample.
Correct. 1 ml of sample, 2 mils of water. If that dilution reads a specific gravity of 1.015, what are you going to report?
That times 3.
1.045. Good. Yep. Now, oh, yes.
So you're actually multiplying the decimal.
Yep.
After the decimal point by the factor, not the.
Just these 3. Correct. Correct. And the instructions are in the lab manual. So if you ever get confused, go to your lab manual. You'll hear me in lab sometimes. You might ask me a question, and I'm going to tell you to go look in your lab manual first. I'm not being mean, but during your lab exam, you get your lab manual. So I want you to learn to use your lab manual. And so you'll hear me say that a lot. Okay? I had somebody once think I was being like the meanest person in the world. I'm like, no, I'm helping you because you will have this for your exam.
So, and we only times it by times the 0.015 by 3 because 1.001 is the specific gravity of water, and that's like
1.000.
1.000.
Yep, is water, is deionized water.
Okay, so we're just taking that out, knowing that urine is mostly water, and then timesing that 0.015 because
Specific gravities can't be like 2s or 3s.
yeah.
It has to be like compared to the water. So yeah.
Is that accurate?
Mm-hmm.
Okay.
Yep. Because it's just based on how the refractometer works.
Okay.
So, refractometer readings. There's going to be a couple times we have to do calculations. This is on your homework also, and it's on the study guides, and it's really likely to be on a quiz. Okay, hint, hint. Protein. Every protein reading greater than 1 gram per deciliter, which is 1,000 milligrams per deciliter, when you dip the urine, you're going to get a protein reading. If it's 1,000 or more, for every 1,000 milligrams, you have to subtract 0.003 for each gram. Glucose, you have to subtract 0.004 for each 1,000 grams per deciliter. Now, the reason we do this is that these are big molecules. Protein and glucose are big. It affects the refractometer, not because there's more of them or it's more dense, but they make it bend more because it hits it, because they're big molecules. So we have to make accommodations for that and do this calculation. Because they're so big, they bend the light too much. And then we get an inaccurate reading based on the size, not the actual mass. Okay, so here's an example. We have a specimen containing 1 gram per deciliter of protein, has a specific gravity reading of 1.032. Now these are all specific gravity on the refractometer. Okay, I'm just talking refractometer now. Specimen containing 1 gram per deciliter protein and a specific gravity of 1.032. The corrected specific gravity is going to be 1.032 minus 0.003 for a final answer of 1.029. Because that's going to accommodate for the fact that we had it bent too far because of the big molecules. A specimen containing 2 grams per deciliter of glucose has a specific gravity reading of 1.028. The corrected specific gravity reading is 1.208 minus 0.008. It's minus 0.004 minus 0.004 because there are 2 grams per deciliter and you subtract 0.004 per gram. And in this situation then it's 1.020. Now we have a specimen with 1 gram per deciliter of protein and 1 gram per deciliter of glucose. Has a specific gravity reading of 1.025. So we take the 1.025 minus the 0.003 minus the 0.004 for a final reading of 1.018. We only calculate this once it hits the 1,000 milligrams per deciliter. If you have 50 milligrams or 100 milligrams or 500 milligrams, we don't change it. Okay? I had somebody once try to like calculate out how, and do all this. I'm like, nope, nope, nope. We only hit full amounts at 1,000. So you don't have to do the ones in the middle. Now, dipstick specific gravity. Wow, say that 10 times fast. Dipstick specific gravity is different. Everything we've talked about so far has been refractometer. Dipstick specific gravity, we look at the ionized particles in the urine attached to the pad, and what they do is they displace the hydrogen ions then. Those hydrogen ions get released into the urine, and that change then, it's an alkaline brothymal blue pH indicator. And as the hydrogen, released hydrogen bind with the indicator, it becomes more acidic and the color changes to green or yellow. So here's what's going on. Our urine has sodiums and potassiums in particular. We're just going to use those, the ionized particles. We're going to put them on the pad. The specific gravity of the pad before the urine, it's all hydrogen ions. After we add the urine, the hydrogen ions are all leaving, and then the sodium chloride. So it's displacement of the hydrogen ions that we're actually looking at. So it's ionic. The pad releases hydrogen ions, absorbs the sodium and potassium. The hydrogen ions acidify the alkaline brothymal blue to a green to a yellow acid color. The alkaline urines interfere with this testing. So if you have a super alkaline urine, if you dip the urine, your pH is 8. It actually affects this pad, in which case we have to add 0.005 to the specific gravity reading of the dipstick. Okay, so procedure for this, we're going to follow the dipstick procedure. We're going to dip it, draw it, blot it, and read it at the designated time. It only measures the ionized particles, so because of that, glucose and protein are not ionized particles, so they are not going to affect this pad. Okay, glucose and protein only affect the refractometer reading. The pH affects this pad. pH does not affect the refractometer reading. We'll draw a chart here at the end of class to go through it all. So for the correction factor for the dipstick, any pH greater or equal to 6.5, we have to add 0.05 to the specific gravity of the dipstick. No corrections are needed for temperature, protein, or glucose. In this situation, refractometer only. Now, yellow iris, some of the instrumentation out in the lab world has this harmonic oscillation. The principle is they use sound waves to measure the density. I'm not going to spend a lot of time on this. Every instrument's a little bit different. Again, when you go out to your clinicals, when you go out to get a job, learn the instrumentation, how it works, what its what idiosyncrasies are. It's really important for you to understand that to know what's really happening. But what they do with this, sound wave vibrations in the solution are proportional to the density of the solution is how that works. Osmometer, like I said, hardly anybody has an osmometer anymore, but the principle is measuring milliosmoles of solute particles per kilogram of water. I'm not going to have you worry too much about this. The one take home from this thing is about the colligative properties of solutions. They're the properties that are dependent only on the number of particles in a solution. So when we talk about okay, I'm gonna get back into this in a couple slides. I thought it was in the next slide. It's a couple slides from now. We'll talk about colligative properties again. So here's just a chart talking about the principle and limitations. These are the two we're gonna use most often in the lab. So these are the two you really, really need to know. Okay. Key terms. Make sure you know your key terms and your objectives. Colligative properties. I'm going to spend a couple minutes here talking about them. When you put salt on your sidewalk in the winter, what does the salt do?
Lowers the freezing point.
Lowers the freezing point. So what's the normal freezing point? 32, right? 32 Fahrenheit, 0 Celsius. Leave it to our country not to understand the breakdown. 32 Fahrenheit, right? And a lot of our salts will take you down to, used to be 25, 20. Well, now we have some really good ones that take us to like 15, right? So it has to be 15 degrees before it's going to freeze. Is kind of the idea behind it. So it lowers the freezing point. That's considered a colligative property. Putting salt in pasta water, it raises the boiling point. Now, I had a chemist one time. I love this woman. One of my students, she was hilarious. And she actually brought me the math. She goes, do you realize for a quart of water, you'd have to add 2 cups of salt to actually make it affect what? I'm like, no, really? So the books talk about adding salt to water. It doesn't really do much. So, because, we don't add a cup of salt to our boiling pasta water. But it still helps you think, add the salt, lower the boiling pressure, right? That's what we're talking about when we're talking about those types of things. Things that affect boiling temperature and the solutes in the solution that are going to affect boiling temperature and freezing temperature. Make sure you know your objectives, and I believe that's it. Oh, more objectives. This one has a lot of objectives in this one. Still more objectives. A lot of objectives in this lecture. Make sure you know them all.